Okay, for the second video in our Grym series, sort of sounds like a horror movie, doesn't it? Actually, I'm kind of regretting saying that now because perhaps that's how it'll turn out, just like a sort of a terrible horror movie. But let's see how we go. So for the second video in our series, I want to look at the Krill 1996 example and just sort of work through the code a little bit, having established some principles in the previous video. So we start off, if you sort of look here, we load up a bunch of libraries that we're going to use. Then as we go down, we define the model. And there's really two aspects to this. The projection function actually produces another function. So you sort of think of all of this code. This is code that's static from projection to projection. So we're going to sort of perform multiple projections or multiple runs, if you like. And this stuff is constant from projection to projection, but anything that changes from projection to projection is down here. There's quite a bit of setup in running one of these things. So let's kind of go through the basics step by step. And then I think what I'll do is I'll run this and run it in a single step debugger so you can actually see the bits and pieces coming together as we go. So we sort of start off by setting up some stuff that really would be constant, fairly constant for a particular analysis. So the number of time steps, the number of age classes, you might want to have slightly variant analyses where you change these things, but broadly, they're not parameters we're going to want to change a lot. So we're holding them fairly constant, or holding them constant, calculating them up front. So number of time steps in a year, the ages, the age classes we're going to model age classes 0 to 7. The actual time steps in units of years. So kind of the first time step is 0 within the year. The final time step is 1. And even though we've got 365 days, the number of time increments, our sort of actual time increments span the days. So the first time point is really midnight of the day before of the first day, and the final time point midnight at the end of the final day. We have to give a spawning range and a monitoring range. This is where we're going to calculate spawning biomass. This is where we monitor the stock. If we give a range of days, we get an average over that interval. If we just give a single, well, it's not day, actually, it's time increment. So remembering that the first time increment is the midnight before, often these things differ by 1 from what you might expect. But that's a sort of a minor detail I'll leave you to work through. Okay, so this ages effectively combines the days within the year with the age classes to get the age at every time point and for every age class. Then we construct the length matrix as from a von Bertalanffy, but this is this restricted growth model that we've sort of inherited from the generalized yield model that assumes that all the growth happens between time increment 0 and 93. And then the weights are just calculated from a power law with these obviously fairly carefully chosen parameter values here. Okay, the bit where it starts to get tricky is calculating things like the intra-annual natural mortality, the within year natural mortality. So remember that all of these things, so the ages, the length, the weights, they're all stored as matrices where we've got columns for age classes, rows for time increments. So in this case, we're just building up an intra-annual natural mortality, and it's just constant. Every individual at every point in time experiences the same natural mortality, and we set that to 1. And then remember, this is the matrix little m's, and we scale that thing by the overall annual natural mortality later in the story. But then we calculate the cumulative mortality with this C-trap-Z function. So if you want to think of that as a cumulative sum, that's fine. What it really is a cumulative trapezoidal rule for those that are familiar with the methods of quadrature. So that calculates this capital M's matrix. And so if this was the instantaneous mortality felt on day, say, 300 for age class, let's say 0, 1, 2, then the corresponding point down here is the cumulative mortality felt all through the year for an individual in age class 2 at day 300. This MSF is just the final row of that matrix and is used for some calculations. So the point is, you've got to set these matrices up and then they'll be used later. And sometimes the easiest way to do this is to start sort of at the bottom. Some of these parameters up here at the top, the number of ages, the number of days, all that, and you can set that up. The spawning interval and the monitoring interval, you can determine those things. Some of this stuff's a little bit trickier, and what you're probably better to do is work out from the projection code that we'll get to later what you need to do for this stuff. Turning to the fishing, the within year fishing pattern, here this FWY is the fishing pattern within year, and it's just a vector. And so essentially what we're going to do is create a vector that's essentially 0 here, and for some chunk of the year, it's 1 and 0 again. And this is essentially defining the fishing season. So that it scales in a rational way, we actually scale it so that the total cumulative fishing mortality, or the sort of the sum or the average over the year, is 1. And this is the variability in survey. So we're going to simulate an initial population structure, have a look at the biomass, and then say, well, if we went out and had a survey, we wouldn't exactly get that biomass. So we're going to sort of simulate the error we might get in a survey, and it's going to have, this is going to dictate the variability. Okay, so the next, this initial stage here of the code, this initial stage all through here, is constant from run to run. We're not changing the mortality from run to run or year to year. We're not changing the within year fishing season or the survey error. Then as we go down here, we've got to generate a maturity and a selectivity pattern. So this ramp ogive function essentially just calculates a ramp. So in both of these cases, it works off you can see here, it works off the length matrices. All right, so they're both, if I can just find my spotlight, they're both driven by length. You're free to set these things up however you like. In this case, they're driven by length. And essentially in both cases, they're driven by this ramp ogive function. And all that does is for a certain length, it has a ramp, so as a sort of a function of, as a function of length in this case, it just produces this ramp function. You give it the midpoint and the width of these things. And in this case, we're letting that midpoint vary randomly. And we're holding the range in each case constant. In the first instance as 12. So the sort of the width of this ramp is held constant at 12 and 10. Okay, the next step is to calculate our instantaneous fishing mortalities, right? So this F's, the little f's, essentially becomes a matrix that's our within year fishing pattern by our selectivity. So we've calculated our selectivities. So for each point, each age class and each point in time, we've got a selectivity. How heavily would this particular, an individual of this age at this time be selected by the gear? But then we're applying to that the fact that the season only operates within some window within the year. And so essentially this gets zeroed out here and we have our selectivity operating in here. So if you sort of looked across a row of this matrix, you'd kind of see that ramp pattern. Okay, so having done that, having generated the instantaneous fishing mortality that an individual would experience, we've then got to calculate these cumulative things and the final row of that cumulative thing. So again, if we've got our matrix of F's, if you pick a point here and you said that's the, the instantaneous mortality that an individual on day 100 in say maybe that's age class 1 or something, the corresponding thing down here is the cumulative fishing mortality that an individual would experience. And so that's the capital FS matrix. And then this final thing, this FSF, is sort of the final row of that matrix, and that's used in some calculations. And the point is, because we're randomly changing our selectivity, that changes every run. We randomly choose our selectivity. That then has a flow-on effect to this matrix through here, which then has a flow-on effect to the capital FS matrix and the final row of that matrix. So this matrix here and this matrix have to be scaled by an annual natural mortality. So in this case, we're selecting a random natural mortality between 0.4 and 1, right? So quite large, really, in this example. And then we scale this matrix by that natural mortality. That gives us this MS matrix. So the sort of the notation is we've scaled by capital M and we're scaling the capital MS matrix. I think, fairly obvious notation there. Okay, so then this is, we're going to randomly choose the recruitment variability. And essentially this is how we've chosen to simulate it. We then do a couple of preparation steps. What this does is it generates, let me just clear the drawings. This generates one large matrix of recruitment samples. Okay, so what we end up with is a whole bunch of recruitment time series, and we've generated something like 1,000 or 1,001 of these things. And then we use each one of those to do a small projection, assuming no fishing, to determine the spawning biomass in the absence of fishing, sort of for 1,000 simulations. And then we take the median of those. This is something that we kind of inherited from the generalized yield model. It's not something I'm a particular fan of because it's not very accurate. 1,001 isn't really enough. You don't get a good estimate of the median. And I kind of query its value in that it's not something that I think we would have in practice, but that's what it is. We also set up an initial age structure. And again, what we're really doing in both these couple of steps is taking some recruitments, projecting them forward in time, down here, and then saying, well, what is that final population structure we wind up with if we've projected those things forward in time, assuming no fishing? So we do that 1,001 times and get the spawning stock biomass. We do it to get the initial age structure that we're going to project onwards for. And this is kind of where the real action starts. Having simulated our spawning stock biomass and our initial age structure, we now generate a recruitment series, and we generate this ahead of time because we're going to use it over and over again from an initial starting point. So if I just clear these drawings, what we've done is we've simulated an initial population structure. We're going to use that to simulate forward again further in time. We're going to use a particular series of recruitments, right? And that's this recruitment series. But what we're going to do is we're going to do this again and again, starting from the same initial structure and using the same recruitments, but letting the level of fishing pressure vary, right? So rather than doing several simulations where the fishing pressure varies, but allowing the initial structure and the recruitments to vary as well, we're holding those fixed. We're just going to vary the amount of fishing pressure. So we pre-allocate a matrix to store some results here in this line. And then we do an initial projection, assuming no fishing, that kind of gets us just one step ahead. This so it takes us one step on from here, and we're going to use that as the basis of as the sort of the first step forward for all our projections. So we calculate at this point the mean stock in the monitoring period. We add a little bit of error to it, right? So we're adding error here on the basis that if we really went out and took a survey, we wouldn't get exactly the right result. So we're sort of saying, well, our survey variability is essentially driven by this B log SD parameter. Let's add a little bit of variability because our surveying skills aren't perfect. So then, having set up this recruitment series here and our initial population structure, what we do in this next block of code is we set the target catch as some fixed fraction of the biomass from our initial monitoring period. Right? We're going to do this again and again. So essentially, we're slowly increasing the fishing pressure, but keeping the recruitment and the initial state the same. So we reset back to this initial projection we've done each time we increase gamma. We calculate our spawning stock, and then we, over a number of years, we essentially, what this does is advances everything along 1 year. So we've got a current, you can kind of imagine there's a current age structure that gets shoveled along. So as we advance a year, those guys at the end of the year that were 0, 1, 2, 3, at the end of the year, the zeros become the ones become the twos, and so on. So we shuffle everyone ahead. We insert some recruitments, right? And this comes from this recruitment series that we've calculated up here. So we're always using the same recruitment series. Then we project forward over the year, repeat the whole process again. This step here, the recruitment depletion, is essentially if our spawning stock biomass falls incredibly low, then we reduce our recruitment level. So we hold the recruitment the same for every projection unless our spawning stock biomass falls particularly low, in which case then we say, well, if we've got a very low spawning stock biomass, we would expect there to be some impact on recruitment, so our recruitment declines. So after we've projected ahead, we then recalculate our spawning stock, and the whole process starts again. We collect here some annual summaries. So there's a whole bunch of stuff that gets collected here. The year, the fraction of the biomass that's taken as catch, the recruitment, so on and so forth. A whole load of stuff just gets recorded and returned from this function. So there's a couple of features here that I just want to emphasize. Firstly, if you look at these, we're in this really simple simulation, we're assuming that our recruitments are always log normal, and we're giving them the log variance is this sigma r, and this choice of the mean parameter, it's actually the log mean parameter. This choice is a sort of this minus sigma r squared on 2 term is a bias correction, which essentially assumes, or essentially gives us unit means. So these log normal recruitments are given a unit mean. And so this is a per recruit analysis. On average, our recruitment is 1. There's one single recruit. And then the rest of the whole calculation is sort of proportional to some observed feature of the population. So if we were to, instead of having this mean as 1, we made it 1,000,000, essentially everything we calculated would just be scaled up by 1,000,000. And so, our biomass during the monitoring period would be scaled up by 1,000,000. So then the catch we take, if we were taking 10%, initially we're taking 10% of just of the biomass that's there if you've got 1 recruit. If you've got 1,000,000 recruits, you're still just taking 10%. So your catch would go up by 1,000,000 because you're taking 10% of what's there, or whatever particular gamma fraction you've chosen to take. So this is a per recruit analysis, and ultimately it's got to be scaled to some known biomass or some known recruitment level. When you run this, effectively this function, let me just clear those distracting drawings. Effectively this function does some initial calculations of stuff that's constant, but then it returns a function that's going to do this computation, time and time again. So when we call this, we do the initial calculation. To actually do the projection, we have to call the sim function. And that just does one single projection ahead for a bunch of different gammas and gives you the results. Okay, I think I'll leave it there, and then we'll have another look in a single step debate.